The greatest determining factor in solubility is the likeness of intermolecular forces. And the likeness being polar dissolves polar, nonpolar dissolves nonpolar. And to illustrate this, I have picked two common examples that people are generally familiar with: vitamin A and vitamin C. Vitamin A is what is called a fat-soluble vitamin. Vitamin C is known as a water-soluble vitamin. And to show why these are called what they are, I'm going to have a look at the structure. In vitamin A, I notice there is only one really polar group here. The rest of these are alkenes. They're double bonded carbons. And in fact, if the end were different, it would in fact be a non-saturated fat, it would look like. Over here, vitamin C has many polarized bonds, and it is a water-soluble vitamin. So what makes this a water-soluble vitamin? Well, it's the polar bonds. Since water is polar as well, it dissolves readily with water. The polar bonds attract each other. With vitamin A, it is not a water-soluble vitamin because it only has one polar bond, and the rest of this is non-polar, so it does not have a lot to bond with water, only one end. So maybe it might be partially soluble at one end, but generally it is not soluble with water. And likewise, the reason that this is not a fat-soluble vitamin is because it has many polar bonds. It doesn't have large areas where there can be London force interactions, so it does not dissolve well in fats. And this is the reason why it's wise to look at what, or to be cautious with, fat-soluble vitamin intake, or doctors warn against it, because since water is the medium by which the body transports different materials, if something is not soluble in water, it's difficult for that to move around, and it would be difficult for the body to get rid of excess of whatever that may be. And if it's a vitamin and I take too much, or if someone takes too much of a fat-soluble vitamin, it's difficult for the body to get rid of it, so they can become easily poisoned by it. But in the case of water-soluble vitamins, the body can easily get rid of them. That's why when people get sick and start taking a lot of vitamin C, people don't generally worry about overdosing on vitamin C, because the body can easily get rid of it. Now, if they're dehydrated or something like that, then maybe they might have some chance of something not good happening to them, but most of the time, nothing serious is going to happen to them because the body can easily get rid of it. Now, another factor of solubility that people tend to wonder about is temperature, and normally they think that temperature has a positive, well, not really necessarily positive, depends on how one looks at it, but normally when people think of temperature, they think that it helps dissolve things to add heat. And generally, or in many, maybe not generally, but in many cases, at least with things that which people deal with in their daily lives, they might find that temperature or in adding heat helps to dissolve things. But that's not always the case. In many cases, adding heat will have a negative effect on the solubility of something and cause it to precipitate. It just depends on the substance. It has to be determined experimentally. It just so happens that many people think that because many times in cooking, people will use salt or sugar, and those things, if you add heat, then it does help dissolve it. And it doesn't necessarily help sometimes it doesn't necessarily help the overall solubility. What it will do is just speed up the process, and that's all. But it needs to be determined experimentally. So there are no overall general trends, I'll say, because depending on what the structure is for certain types of bonds or families of molecules, there certainly is a trend, but it's not necessary to know. And one more thing to go over is just the solubility of gases. Now, gases, the two main determining factors will be temperature and pressure. Pressure is very simple. For pressure, if I increase the pressure, then more gas will be dissolved. This is called Henry's law. C is equal to the concentration, K is equal to the constant for the solution, and P is equal to pressure. And if I notice, it's directly proportional. So if I have 1 atmosphere and now I increase the pressure to 2 atmospheres, then twice as much gas will be dissolved in there. And this is a picture of soda. Soda is generally, I believe, at 12 atmospheres, so 12 times the pressure it's bottled at. So there is 12 times as much gas dissolved in that soda as there should be at the atmospheric pressure. That's why when people open it and leave it out for a while, it goes flat. All of the gas eventually escapes. And one general trend there is for temperature in gases is that the lower the temperature, the more gas can be dissolved in it. And that should make sense because gases have a lot of kinetic energy, and the less kinetic energy they have, the more that can be dissolved in that solution.